All right, let's look at the biangular region originating at the vertex B. So we continue going around in the counterclockwise. Well, last time we showed the biangular region starting at A, going from A to C. We'll start drawing a great circle from B to A now, go around to the other side, B prime, and then come back via C prime, and you'll get this biangular region consisting of a spherical polygon with two angles. And the angle you can just see by inspection, and this is so hard to see without a three-dimensional program like SketchUp, but I think it's really useful to draw these things in SketchUp and get a three-dimensional version of it that you can rotate around and see from different perspectives. So that's the second biangular region. And here's the third biangular region. You continue your counterclockwise rotation around here and draw a great circle from C to A, around to the other side at C prime, and then back through B prime. And again, the angle is just the angle pi, or 180 degrees, minus the angle at C here, gamma. So it's just pi minus gamma. And the area of this region is just that angle, pi minus gamma, times 2 times r squared, the radius. So if this angle weren't the short angle but went all the way around, so it was 2 pi, it would be 2 times 2 pi, which would be 4 pi, r squared, which is the area of the sphere. So that's the third region right there. So you see that you get 3 biangular regions to go with the triangle itself and the inversion triangle. And the interesting thing about that is that it covers the entire surface of the sphere. So the sum of those 3 biangular regions and 2 triangular regions is equal to the area of the sphere. And then you're going to use that to show relationships between the angles and the areas of the geometric figures. And let me just show that next. All right, let's go back to Euler for a second here. And there he is. So basically, we showed that we can cover the entire sphere with 5 regions defined by any arbitrary triangle ABC. So we'll just use the notation S sub ABC, the area of ABC. And then there's another one, which is the inversion of SABC on the opposite side of the sphere, called SA prime, B prime, C prime. Those two are equal. They're formed by the exact same angle. It's just one is the inversion of the other through the center of the sphere. And so SABC plus SA prime, B prime, C prime is just 2 times SABC, 2 times the area of the triangle. And that's the first part of the partition, those 2 triangles. And then we get 3 biangular regions which cover the remainder of the sphere. The biangle AC, that's the biangle at A, AC, A prime, B prime, at vertex A, having angle pi minus alpha. Alpha is the internal angle at A. So we just call the internal angles at the triangle vertices A, B, and C, alpha, beta, and gamma. Sorry, that sometimes I use capital gamma. Sometimes I use small gamma. A little bit inconsistent of that because of different softwares. Forget it. But anyway, then there's the part 4, the biangle at B, which just goes B, A, B prime, C prime. Those vertices of those points define that biangle. It has angle pi minus beta, pi minus the internal angle at B, and an area given by 2 times pi minus beta times r squared. And then 5, the biangle at C, SCB, C prime, A prime, at vertex C, having an angle pi minus gamma and an area of 2 times pi minus gamma times r squared. So basically, every time you draw a triangle on the surface of a sphere, or every every spherical triangle ends up having a partition of the entire surface of the sphere into these 5 kinds of regions. And that, from that, you can generate a simple equation. Okay, the next thing is to write down the whole equation, and I got to be careful here with the equations because the watermark, as they call it, will end up covering up my conclusion or something. I don't know, but I know I'm okay up here at the top. So we divided into 5 regions, and then we set that equal to the entire area of the sphere. 4 pi r squared is the area of the sphere for any radius r. And then these are the 5 regions for any triangle ABC. And that can be expressed in terms of the internal angles, because of the internal angles of those biangular regions are pi minus alpha, pi minus beta, pi minus gamma, all times 2r squared to get the area of those biangular regions. And then this is 2 times ABC because the surface area of ABC and the surface area A prime, B prime, C prime are the same. Then you can just solve this for alpha, beta, and gamma, 3 internal angles of the triangle. And you just follow the kind of obvious algebra through here, and you get the sum of the internal angles of any spherical triangle on the surface of a sphere is alpha plus beta plus gamma. The internal angles at vertices A, B, and C of any random triangle is pi, or 180 degrees, plus the surface area ABC of the triangle divided by the r squared. So essentially what you see is that, let me just raise that up just in case it's not covered, in case it gets covered by my watermark here. How do I do that? Let's see. Let's just bring this up here like this. Okay, the sum of the angles, alpha plus beta plus gamma, equals pi plus SABC over r squared. Now recall, what happens if, well, let's look at what happens if r goes to infinity. In other words, the radius of the sphere is infinite. Then the surface becomes perfectly flat. There's no difference between a plane and a sphere with an infinite radius. And then SABC for a finite triangle goes to 0, and alpha plus beta plus gamma equals just pi, or 180 degrees. So that's Euclidean geometry. But here you get sort of a free proof of that. But you also get the proof or the formula for the sum of the internal angles of a spherical triangle, which is in general always greater than 180 degrees, and will increase as the area gets larger. Put that back, and hopefully you saw that in spite of my watermark on my free demo version of whatever my program is called there.